Hello, everyone. I'm Kylie, a PhD student from Syracuse University. I'm happy to present our paper, TopoShot, uncovering Ethereum's network topology, leveraging replacement transactions in the IMC conference. This is a joint work with my advisor, Professor Yuzhe Tang, and my lab mates, Jiaqi, Chen, Yibo, Wang, and Xianghong. In practice, a larger blockchain network usually contains more than thousands of nodes. And we want to know what the topology looks like. There are two main reasons to know a blockchain's topology. First, it can help us understand the security of blockchain. For instance, what if a network's topology is a star? Knowing this, an attacker can choose to disable the central node to separate all other nodes and to easily bring down the entire network. Also, other attacks like eclipse attacks and the anonymization attacks can benefit from knowing the network topology. Second, it can also help us understand blockchain's performance, including the mining pools and transaction relay service. For example, if two mining pools are connected, the miner can disseminate his mined block to other competing miners more quickly, so that his mined block has a better chance to be included in the longest chain. In the existing literature, there are measurement studies on the nodes and edges in Bitcoin networks. Other works detected the edges in the Monero blockchain. On Ethereum, the only related work measures only the nodes. So far, there's no measurement on the edge in Ethereum networks. We propose TopoShot to fill this gap. TopoShot is the first work that successfully uncovers the edge in various Ethereum networks, including both Testnet and the Mainnet. The key idea behind TopoShot is to repurpose transaction replacement and eviction in Ethereum's memory pool to measure the network edges. Next, we will give the preliminary of Ethereum memory pool. In the Ethereum blockchain, a memory pool is used to buffer transactions that are not included by the miner. Ethereum supports different kinds of transactions determined by the nonce. For instance, the right finger shows 9 transactions sent from one account, and each associated with a number called nonce. Transaction 1, 2, 3 are included transaction. Transaction 4, 5, 6 are pending transactions. Transaction 8, 9, 10 are future transactions because of the nonce gap. Future transactions cannot be executed by the miner until they become pending, so they are unprofitable. Notably, if two transactions are with the same nonce, but with different gas price, they are called replacement transactions. A transaction's gas price is the amount of Ether that the user is willing to pay for the single unit of computation. In Ethereum's memory pool, to accept a new replacement transaction, the new gas price must be at least 10% higher than the old one. The design of replacement transactions allows users to accelerate the inclusion of their transactions, and setting the 10% threshold is to defend against spam transaction attacks. When the memory pool is full, in the eviction policy, to accept a new transaction, the new gas price should be higher than the lowest gas price in the memory pool. This eviction policy aims to increase the mining profit. Now let me demonstrate how TopoShot works in detail. Consider in the network, a measurement node M who is connected to node A and node B wants to detect if node A and B have a connection. Node C represents the rest of the node. In the first step, node M sends a pending transaction TXC to node A using a low gas price 0.1. Then TXC will be propagated to the entire network. In the next step, node M sends a lot of future transactions to node B using a high gas price 0.2. The future transactions will overflow node B's memory pool and evict TXC. Then the future transaction will be discarded because they are unprofitable. Next, node M sends a replacement transaction TXB to node B with a slightly lower gas price. Node B will accept TXB, and the other nodes will reject TXB. Similarly, next step, node M sends the future transactions to node A to evict TXC. In the last step, node M sends another replacement transaction TXA to node A with a slightly higher gas price. Now, node C will reject TXA, but node B can accept TXA. So node M check if it can receive TXA from node B. If so, node M knows node A and node B have a connection. This is how the basic approach works, but it is slow to measure a large network. To improve the efficiency, TopoShot uses a pairwise approach to measure multiple pairs in parallel, which can reduce the total measurement time. Please refer to a paper for the details. To evaluate TopoShot's accuracy, we set up a controlled environment by running one node in the testnet. Then we use TopoShot to measure the connections and report the metrics of true positive, true negative, and false positive, false negatives. We vary the number of future transactions used in the approach, and the result shows the more future transactions we use. TopoShot will have fewer false negatives, namely have a higher recall. This can be explained as some of the neighbors in the testnet configured a larger memory pool. We also vary the number of nodes measured in one round, and the result shows a larger group size will reduce the recall. Overall, TopoShot does not have any false positives, such achieves 100% precision. We use TopoShot to measure Ethereum testnet. For the Robusten testnet, we measured more than 500 nodes and detected more than 7,000 edges. The node degree distribution is presented in the finger on the top. It shows that most of the nodes have less than 50 neighbors, and a few nodes have more than 100 neighbors. We also compare the testnet's graph properties with random graphs, and the result shows testnets have a smaller click and modularity, which implies testnets are more resilient to network partition attacks. We also observed similar results on other testnets, including Ranking B and Goerli. Last but not least, we measure Ethereum mainnet. However, measuring the entire mainnet is expensive for TopoShot and will cost more than $60 million. We thus only measure a subnet that consists of critical nodes. We define critical nodes as nodes belonging to mining pools and transaction relay service. We use a heuristic approach to discover critical nodes. We scan the mainnet by peer discovery messages and select those nodes whose version name is highly suggestive. In total, we discovered 8 different mining pools and 2 transaction relay services. So we configure our measurement node to selectively connect to these services and start measuring the connections. To minimize the interference, we carefully set a low gas price of our measurement transaction so that we only evict 10% of existing transactions in the memory pool. Then after each round of measurement, we resend those evicted transactions to the target node. Our mainnet results have interesting findings as shown in the table on the top. First, transaction relay service R1 connects to all other mining pools. Second, transaction relay service R2 does not connect to any other service. In addition, all mining pools are mutually connected. This result suggests the critical nodes on the mainnet have biased neighbor selection strategies. We also summarize the measurement cost, time, and duration in the table on the bottom. Please note that only the mainnet measurement charges us $. In conclusion, TopoShot is the first measurement study that uncovered Ethereum topology. This is a novel and effective measurement approach by repurposing transaction eviction and replacement in Ethereum memory pool. The local validation shows TopoShot achieved perfect precision and high recall. We applied TopoShot to measure real Ethereum networks and found interesting results. The result shows the testnet are more resilient to network partition attacks than random graphs. And the critical nodes on the mainnet have biased neighbor selection strategies. These are the related work referenced in my presentation. Thank you for your attention. If you have any questions, please feel free to ask me or Dr. Tang.